focus.
Kepler's first law is the, what does it say? Okay, so it's dealing with elliptical orbits of the planets, elliptical orbits, and it says more than that, so let's see here, here's an elliptical orbit I'll draw, planet, and the sun is located at one focus. Remember, an ellipse has two foci, and the sun is at one of them. So that's the first law. Kepler's second law. Go ahead.
An imaginary line from the sun to the planet sweeps out equal areas and equal time.
Okay, so we're dealing with equal areas. So if I was to draw the orbit again, I'm going to focus, and then the planet. Right, it goes around, we would see that this imaginary line sweeps out an area equal to the area between these two imaginary lines, and all such areas are equal. That's the law of equal areas. So long as T1 and T2 are equal. If T1 equals T2, then area 1 equals area 2. This is area 1, this is area 2. And that means that the planet is going faster when it's over here, and it's actually going fastest when it's at what point? We gave a name for that. Perihelion. Good. And then it's also going its slowest when it's over here, and we call that aphelion. Right, so those are the first two laws for Kepler. And then we looked at Kepler's third law. Third law, which says what?
The square of the ratio of the periods of any two planets revolving about the sun is equal to the cube of the ratio of their average distances.
Right. So the square of the ratio of the periods, where A and B are planets, equals the cube of the ratio of their average distances. Okay? And maybe let's just kind of simplify this equation a little bit. Maybe think of it in another way. So I do that. That. Now let me bring all the A quantities to one side. And so what we see actually is that t squared over r cubed is the same for every planet. So t squared over r cubed then is constant. Right? And that goes for all planets. T squared over r cubed will be the same value. So maybe it's easy to remember it that way. Now, let's do this. I'm going to draw. What happened?
Nothing happened. I'm good. Just got aimed at once more.
You got what?
By my cookie salesman. Horrible.
We got the sun. We got Earth. And we got Mars. And we got this. What is that? The moon. And we have this, which is one of Mars's moons, right? Mars has two. One's called Phobos. I don't remember the name of the other one. Is it?
Yeah.
You sure?
Yeah.
Okay. The most, the other
it's
one.
What's the planet with the most moons?
Jupiter,
Mine doesn't have. 27.
is it 61?
61.
It has a lot.
Oh,
How many does Saturn have?
I thought
I
it
had
was
no
64.
idea.
I thought it was
48.
Okay.
Why are you noting?
Yep, I said that.
Oh, well, that, okay.
All right, and now I'm going to draw one more thing.
Satellites.
A satellite, right? It could be a weather satellite, GPS, DirecTV, doesn't matter, satellite. There's a bunch of them up there. All right, now, I want to ask some questions here. Could I use Kepler's third law to compare Earth with Mars? Yeah. I would just make A Earth, and I would make B Mars, and I'm good to go. Could I use Kepler's third law to compare the moon to Earth? No. Why not?
You're asking me.
Yeah.
Because they're not revolving around the same thing.
Right.
Or orbiting, I guess.
Yeah. So no, because they not orbiting same object. So if I wanted to compare the moon, or if I wanted to know some information, let's say, what could I compare? I could compare the satellite of the moon, right? I could compare the moon and DirecTV. That's a yes. Because they're both orbiting Earth. Right? Both orbit Earth. So that is a yes. So that's important that you realize that. You cannot compare objects that are not orbiting the same thing with Kepler's third law. So if I wanted to know something about Mars's moon, I would need to know something else about another satellite going around Mars, one of its moons or another satellite or something. Okay? Everybody got all that? Now let's do something else. Everybody turn to page 173 in the textbook, please.
So it's true, you can lie to the season pass and that's right.
He said so, so I was saying.
Jack, would you be able to give me a discount if you bought it for me? Really?
He's lying, he's doing good.
I think it's like only $10 off. Like if I buy these, I get you bought it for me. Yeah.
You're gonna try it. Too much. I just fired. No. I just went. Fired. That's kind of looked at the future. Hershey Mark fired.
Okay, so now use the data in that table. I would like somebody to tell me the value of this green line right here.
Are we on the right thing?
I think so. Maybe. What page was it?
173.
Oh, 173, 273.
I was gonna say, I saw the foot, I'm like,
Yeah,
No,
that's fine.
Sun, Earth, Mars.
Oh, so the sun is the thing, not the green point. The sun is
Yeah, this is the sun. This is the outline of the sun. What? 6.96 times 10 to the 8th meters. Okay. Does everybody see that number on the table? Somebody give me the value of this blue line.
1.50 times 10 to the 11th.
What is it?
1.50 times 10 to the 11th meters.
Does everybody see where we got that?
Yeah.
Somebody now give me the value of this green line.
6.38 times 10 to the 6.
Now let me get the value of this blue line.
0.28 times 10 to the 11.
And let me get the value of this green line.
3.4 times 10 to the 6.
So does everybody see where we're getting those values from? What they
Yes.
represent? Okay. So now if I did Kepler's third law, between Mars and Earth, what value goes here? RE.
6.38 times 10 to the 6.
What was the question?
What value goes where RE is? Okay, that R is the radius of what? The orbit. Right? This is the radius of the orbit. So Kepler's law does not want the radius of the planet. It wants the radius of the orbit. And this number would be, okay, so make sure that you realize the difference and what number goes there. It's important. Does everybody see that? What number to pick there? You want to pick the radius of the orbit, which is the distance between their centers. Now this number, 1.50 times 10 to the 11th, is from center to center. So it already includes radius of Earth, I better write this, includes 6.38 times 10 to the 6th and 6.96 times 10 to the 11th. Right? Because it's
The time.
the whole distance from
Yeah,
center to
yeah, yeah.
center.
Right.
Sometimes people want to think that the blue number is just surface to surface and it doesn't account for the radii, but it does. Okay. Questions on any of that? One more thing we got to look at.
So the 1.5 and 2.8 are the radius of the Earth,
Radius of Earth's orbit from the sun.
and is the period of Earth's orbit.
Period is 1 day or 365 days or 1 year, whatever unit you use. All right, one more thing. Let's say that now we're looking at the Earth. And this is Earth's moon. And here is the DirecTV satellite. Okay. If I wanted to know the altitude of the satellite, what does that word mean? Altitude.
The height above the surface of the Earth.
Right, the height above the surface of the Earth. So really, I want to know this height. Okay, we'll call that the altitude. So what is the altitude of DirecTV satellite? Okay. If I wanted to use Kepler's law to do that, Kepler's third law, I can use the moon, right? I could use the period of the moon squared over the period of DirecTV satellite squared, equals Earth, or the moon's orbit cubed over DirecTV satellite orbit cubed, right? If I know these, I can measure these because they're times, and I know that distance, then I can calculate this. But if I want to get the altitude of the satellite, how do I get it with this number?
You add the altitude and the radius of the Earth.
We got to subtract them, right? If I calculate this value, then that gives me from here to center, right? This is RDTV,
The offset of that is.
right? Center to center. To get the altitude, I need to then, so I need to take RDTV minus radius of Earth. So I need to subtract out this extra bit in order to get the altitude. That's just something to kind of remember, okay? Make sense? So that's what that video is actually showing us, is a demonstration of that. Now, Newton was the one that determined that figured that out. But what Newton knew is he put it like this: force between two masses. Anybody know what that symbol means in a mathematical context? Huh? It's alpha, it's Greek letter alpha. So it's proportion to m1, m2 over r squared. So the product of the masses divided by the distance between their centers squared determines the gravitational effect on two objects. So what if one of those guys got really big like the sun, then one of these numbers would get really, really high. And then that force would get really, really large. And then, right, somebody's going to pull somebody else. By the third law, they're actually pulling each other. But it's also influenced by the square of the distance between them. So the further apart these guys get, the greater becomes the denominator, the weaker is the force. Okay? The closer they get, the greater is the force. So there's actually a force of gravity between them. Actually between all of us. Right? If it was strong enough, we would all just be clumped up in the middle of the room together. Right? But now there must be a way to figure out what is that value. Newton knew the relationship, how it varies with mass and distance, but he didn't know the value. This is where we come to a guy named Henry Cavendish, 200 years later. He does an experiment that is basically what that video is showing us. So let's say that we were looking down on that apparatus from the video. So you have a bar, here it is, and it's hanging from the ceiling. So we're up at the ceiling looking down. So this would be the center where the string is. Then you have a mass here, and a mass here. And then you have a big lead brick here. A lot of mass, a lot of matter there. And the same mass lead brick here. So that's going to cause this thing to want to rotate. It's going to rotate this way. So let's say it rotates so much, and then we are able, and it stops. So therefore, we're able to measure this distance, and let's say this distance is a meter. Let's say the mass of this is, we'll call that M1, is 1 kilogram. We'll call this mass 2, and just for convenience, we'll also say it's a kilogram. So now we have the distance and the masses. So what Cavendish found was that if you were to separate these kilograms by a meter, and then you could measure that force. So what he did was, if we wanted to make this proportionality an equality, we would need to have a constant, proportionality constant, And then that would allow us to calculate the actual value for F. So that's what Cavendish ended up doing, was he actually ended up calculating that constant. And so if we had, and we're going to give this constant the value G, capital G. So let's say that we had 1 kilogram separated to another kilogram by a distance of 1 meter. What Cavendish found is that the force is actually 6.67 times 10 to the negative 11th newtons. So if I were to separate these kilograms by 1 meter, so here's about a meter right there, the force between them is 6.67 times 10 to the negative 11 newtons. So that's very, very small. It's a very, very small amount of force. But by doing that experiment, Cavendish then found out this value. So G is called the universal gravitational constant. And it has the value of 6.67 times 10 to the negative 11. And the units are newtons, meters squared over kilograms squared. So it's a proportionality constant. You could think of it as like the strength of gravity. So now, if knowing this constant, you could calculate the gravitational force between any two masses. All right, last thing. Now, this is the sun and the earth. The sun pulls on the earth with a force equal to the force of the earth pulling on the sun. That's Newton's third law. That's also Newton's law of gravitation. So what we have is this force between them is equal to G, mass of earth, mass of sun, over distance between them squared. The earth is also orbiting the sun, and we can approximate that orbit as a circle. It's very, very close to a circle. So that means that this force on the earth is actually a centripetal force, and we know from chapter 6 that equals mv squared over r, where the mass here is the mass of the earth. So we can also say that this force exerted on the earth is equal to mass of earth v squared over r. So this is Newton's law of gravitation, and this is Newton's second law for rotation, or for circular motion. But these quantities are equal because it's the same force. So we could say that G, mass earth, mass sun over r squared equals mass earth v squared over r, because it's the same force. Now v is also equal to 2 pi r over t. That's how we measure the speed of an object moving in a circle. So I'm going to put that v in here for v squared. So we're going to get G, mass earth, mass sun over r squared equals mass earth 4 pi squared r squared over t squared over r. Right, I substitute that in there. Now, if we look at this equation, mass of earth is in the numerator on both sides. So that cancels out. And we can also simplify this side a little bit more because we got an r in the numerator and an r in the denominator. So we'll get rid of that, and that gets rid of the squared. So now we have this. Okay. Now I'm going to bring t squared over. So there I'm going to get G, mass of sun, t squared over r squared is 4 pi r squared. And we're going to keep moving things around here. I'm going to bring the, this is not squared anymore, it's just r. I'm going to bring the r over. So that's G, mass of sun, t squared over r cubed equals 4 pi.
So where'd the pi squared go?
The pi is squared, 4 pi squared. And then I'm going to bring G mass of sun over. So t squared over r cubed equals 4 pi squared over squared G mass of sun, and that's it. Why did I do that?
That's the ground.
G is the gravitational constant. What? Yeah, this is Kepler's third law. Kepler's third law, which he came at by just playing around with numbers, right? He found it by just playing with Brahe's data. And we said at the beginning that Kepler's third law is a constant, right? T squared over R cubed is a constant. 4 pi squared G is a constant found by Cavendish. Mass of sun is constant. So what Kepler did by playing with numbers, Newton did by using physics, right? He used his two laws, and he actually proved Kepler's third law. He found that relationship, which is what Kepler found. So you don't have to do that, but I want you to see that. That's what Newton did that.